Good morning, physics. Today is Tuesday, May 12th, and today we're going to be talking about the motion of the Earth's surface. Now, with this, this is sort of our start on talking about earthquakes and seismic waves. We've talked about waves in general going through matter, and now we're going to look at it. This will be sort of the last section of the year for us before we sort of get into our final project. And with this, what's sort of going on is we're going to be looking at how waves and seismic activity are related, and same with earthquakes. So what we're going to start off with is talking about how the Earth's surface moves. And with this, I think it's important to sort of understand the compositional model of the Earth and sort of like the idea of the three primary layers of the Earth. And so with the three primary layers, what we have is we have the crust, which is sort of the part that we're on. It's mostly stone and dirt and sort of all of those types of things, bedrock and various stuff. It's found on the ocean's floor. It's found sort of mountains all around us. We're standing on the crust, and that's sort of an important thing to keep in mind. It is also the thinnest layer of the Earth. And then below that, we have the mantle, which is made up of high temperature, made up of molten rocks and that type of thing, where it's sort of the majority of the Earth's volume is made up of the mantle. And then within it, we have the core, which is mostly iron. It's what sort of creates our magnetic field of the Earth, and it is very dense and high temperature down there. So what we're going to be mostly looking at during this time is the crust, and with the crust, there are a few different types of interactions that go on. So with a, let me actually just move this up. So with our crust, there are a few different, basically it's made up of tectonic plates, which are basically giant, if you think about it, puzzle pieces. So our crust itself is made up of puzzle pieces floating on the mantle. And I say the term floating kind of loosely, where they sort of fit together and rub against each other and are constantly moving. And while we have this sort of constantly moving motion, there are three different types of plate boundaries, so different ways that the plates themselves sort of meet. And those are divergent, which means that they're going away from each other and they produce sort of a tension stress from each other, basically pulling the stone and the material apart away from each other, as well as usually there's some volcanic activity going on that creates new crust in this area as the mantle wells up and cools. The next type that we have is what is called a convergent zone. And a convergent fault line, basically what happens is, this is usually what occurs at a boundary between an ocean and land. You have the continental crust, which is less dense, but there's a lot more of it comparatively, and then you have the oceanic crust, which is more dense. And what happens is because we have the different densities, you have the continental crust that sort of just floats on top, while the oceanic crust sort of sinks down under the ground, which ends up sort of causing more of that oceanic crust to enter the mantle and sort of heat up, and that creates some volcanic activity on sort of the continental side of things. And then the last one is what's called the transform, where you basically have your two faults just sort of going at each other in opposite directions, and they just sort of rub along and they just pass by. It creates a lot of earthquakes, but there's not really any particular volcanic activity because you don't have any mantle getting exposed or things going into the mantle, and so it just ends up making sort of a rough sliding motion. Now, boop, boop, boop. Now with this, one of the key things that sort of goes on here is, if we think about it, we have these different sort of types of margins and all of that. And if we sort of look at the different types of ways to cause stress to rocks, one of the things that sort of happens is we end up sort of can relate the type of boundary based on the type of stress we should expect to see most prominent. Now, this doesn't mean that there isn't going to be other types of stress happening at that boundary, but it means that there's likely going to be more evidence of one particular type of stress than any other, depending on the boundary type. So one of the key ones we have, shear stress. If we think about it, if you take a look at our boundaries, shear stress, the idea is they're moving in opposite directions. If you think about it, that would be most likely like the transform boundary between two tectonic plates, where you have your plates shifting side to side. That will definitely cause a bit of stress to the rocks as sort of shearing. And then if you look at the other sets, we have tension, and if we look at it, they're going apart, so that would be a divergent boundary location where you'd most likely see that type of stress, that tension within stone. And then last but not least, we have compression, which would be at a convergent boundary where you have two plates running into each other and sort of pushing into each other and sort of expanding. Usually, if it's too continental, you'll see a lot of that because they'll be pressing together, and because they're both the same density, they'll just be sort of pushing up and up and up. Which is what you can sort of see in the Rockies. But if it was oceanic, then it would go down, and there'd still be a lot of compression, but then there's sort of different things happening. With that idea, it's sort of a good idea to sort of go on to the concept of seismic waves. Now, we've talked about sort of two key types of waves. We have longitudinal waves, and we have transverse waves. Now, there are a bunch of different types of waves there's sort of two key types of waves that we sort of consider that happen on the Earth's surface when an earthquake occurs. We have P waves and we have S waves. Now, in these two scenarios, those are both S waves, and they're what would be considered transverse waves because the motion of the Earth is sort of perpendicular to the direction of the waves. In both cases, because we're dealing with 3 dimensions rather than just 2, you can have the wave going this way and it's shaking back and forth like this, or you can have the wave also going this way, but instead it's now sort of doing like your normal water waves. And then with P waves, they're longitudinal, and so they act sort of like a slinky. If you send a pulse down, stretch out a slinky, and you sort of like combine some and just sort of send shakes down, that would be a compression wave or a longitudinal wave, which would be considered a P wave. And one of the key things to sort of think of when you have these types of waves, P waves, they're pressure waves, so they're sort of that longitudinal, but they're also the ones that generally reach first. So when you have an earthquake, there are sort of 2 sets of waves that come. There are the P waves, and then there are the S waves, and then there are the aftershocks. The P waves hit first, and usually are the faster moving types of waves. And then the S waves, the surface waves, are the secondary waves arriving next. And that's usually why you have animals that are able to predict a earthquake is about to happen, is they notice the motion of the P waves, those compressional waves, and then the S waves come afterwards. And so we're not as attuned to the change in waves or the feeling the P waves, that when the S waves happen, that's really all we personally notice, but animals tend to notice the P waves as well. And so here's a nice little diagram of these waves. So they have their compressions and rarefactions. Basically, there's parts where the matter has compressed really close together, and then parts where it sort of ends up spreading out as the wave moves through. So, with that idea, this is sort of a brief overview of how earthquakes work. What we're going to end up doing tomorrow is looking how can we use these waves, these P waves and S waves, to make predictions and sort of figure out some fresh things. So that is all for today, and what you're going to do is just read through this section. It is Lesson 2, Explore, Explain 1. You can skip this hands-on lab, but sort of go through, read it, take some notes, and answer all of these questions. And as always, you know where to find me if you have any additional questions or if there's any confusion. So, have a nice day.